would like to thank organizers for opportunity to present our work, which is done at Lancaster. And it's amazing to be here at Cargese and see this amazing scenery. So I will talk about probing quantum fluids using mechanical oscillators. And underneath, it's actually there are two subtopics which I will be talking about, which I offered organizers to talk on each of them, on one of them, and they didn't reply, so I'm going to talk on both of them. So first one will be visualizing quantum turbulence in superfluid helium-3 using quasi-particle. Essentially, it's work about visualizing quantum tangles. And second part of the talk is real-time interaction of nanomechanical resonators with quantum vortices in superfluid helium-3. So we will try to use mechanical oscillators, bridges, to look at individual vortex, and a long-term aim is to determine Kelvin wave cascades directly. So this work been done at Lancaster Low Temperature Group. A lot of people are involved. So firstly, I would like to thank Sergei Kafanov, who most of the experimental work is driven by him. And the nanomechanical beams work was driven by PhD student Amy Lester. The helium-3 visualization is done by Sion Noble, who was PhD student and then started to became research associate as well. Most of the, if you see beautiful graphics, it most likely been done by George Pickett. We have a lot of collaborators, and some of them are here in the audience, and I'll name them as we will be going through my talk. Our work is funded by the EPSRC, Engineering and Physical Science Research Council, and EMP European Microkelvin platform, which I would like to advertise. We have obtained extension, 6-month extension until end of the year, and it offers user access, so you can apply to come for 3 months and work, and everything will be paid to work on, for example, in turbulence. The places where you can come, for example, is you can look at the map. There are several places, but it is in UK. It is, for example, Lancaster, our lab. Helsinki is a lab who is doing turbulence as well, and we collaborate wide in France, for example, with Grenoble. But you can only access it transnationally, so if you're from France, you can't come to France. So please take a look at the website and talk to me during the conference. So most of the work is done in helium-4 and helium-3, so I would like to introduce it. So first of all, we have pressure temperature diagram, and helium becomes only as a liquid at from 5 Kelvin, then at about 4.2 Kelvin at 1 bar, it becomes liquid, and you can cool it down to 0 temperature and it will still remain liquid. And to get solid, you need to pressurize it so it doesn't have triple point. And below about 2 Kelvin, it becomes superfluid, so it can flow without viscosity. So this is normal helium-4, which most of you already heard about. What I will introduce as well, I introduce helium-3, its little brother. And if you look at the phase diagram here in zero magnetic field, it actually becomes superfluid at temperature on the order of 1 millikelvin, which is 3 orders of magnitude lower than in helium-4. It as well, it depends on magnetic field. So by changing magnetic field, you can alter the phase, superfluid phase from A to B. And mostly where we work in superfluid helium-3b at very low temperature, where at least 10 times below TC, where it remains superfluid, and in ballistic regime. So this is quite essential. So I will try to explain as well why why we bother to cool down 3 times lower, but it offers some things which helium-4 doesn't offer. So let's recoup helium-3b. It's much more complicated. I will just give you an essence. So it becomes superfluid below 1 millikelvin. It can be treated as neutral superconductor because pairing is BSC. It has spin 1/2, so it's actually reminds physics. Essential physics is very similar to superconductivity, but we don't have electrons. We have helium-3 atoms. It's extremely pure because at our temperature you will have one helium-4 impurity in 10 to 2000 atoms. So all helium-4 impurities actually are frozen on the walls. And because it has an isotropic gap in helium-3, pseudo-isotropic, density of quasi-particles drops exponentially. And where we work, excitations are ballistic and mean free path virtually infinite. Effectively, it can be kilometers, but it's definitely much larger than our cell of about several centimeters. Let's take a look at vortices. They're similar to helium-4. They're formed by 2 pi change around wave function around the core. So vortices are singly quantized, and quantum circulation is h bar over 2 m3 because Cooper pair is formed by 2 helium-3 atoms. So unlike in helium-4, it will be m4. Here is 2 m3, and then superfluid flows around the core with velocity which proportional is 1 over r, similar to like you have in helium-4. So they're topological objects, so they can either end on the walls as a semi-loop, they can propagate as a vortex rings, and the velocity of the ring is inversely proportional to its diameter. For example, for 5 micron ring, it will travel at 10 millimeters per second. If you agitate condensate enough, you will obtain vortex tangle. So it's so-called quantum turbulence. And just to reiterate in helium-3b again, that if temperature is high, the normal component is at rest. One can use nuclear magnetic resonance and vibrating objects to detect it. But at low temperatures, it's ballistic regime, and then one can study turbulence there using vibrating object like we do, or you can a nuclear magnetic resonance in helium-3, which is done in Helsinki lab. Right, so it requires quite a bit of machinery. It's not perhaps as impressive as a Shrek machine, but this is our cryostat, so it's quite large, and we have about it's heavy, so it has about 60 tons of concrete in order to isolate it mechanically, and then we have a huge pumping lines to get to low temperature. Let's take a look inside. So we have initially it's room temperatures, and we use liquid nitrogen to pre-cool it. Liquid helium is our starting point, and then continuously we can get to about 2 millikelvin. Okay, so we have we have a world record for dilution refrigerator in Lancaster, and the nuclear stage can reach 5 microkelvin, and in our cell it's about 100 microkelvin. It's demagnetization of copper in a magnetic field. But it's one shot measurement, so we do measurement, it warms up, then we do it again, we repeat it. Okay, so this is a mixing chamber of dilution refrigerate, and this is a cell which has a copper plates and cell itself. Let's take further look inside. So if you have a cutout, we have a copper plates which use as a refrigerant. We have some silver powder in order to make a huge surface area to connect to the cell. Cell itself have quite a few vibrating objects, so there can be vibrating grids and can be set of vibrating wires which we use as a detectors. We as well have tuning forks, and grids can be either rough or smooth, several geometries. So let's take a look how it works. So idea behind vibrating wire is following. It is a superconducting loop in magnetic field which can oscillate. So we apply current, and due to Laplace force it will start oscillating. Laplace force pushes back and forth, and now since you have a Laplace force, it will actually in magnetic since you have now wire moving in magnetic field back and forth, you'll obtain a Faraday voltage which you can pick and measure, and then it show in a frequency. You will have a resonance peak, and height of the peak is inversely proportional to the width. So if you have a quasi-particles coming, they normally scatter and they fly away. So we can plot typical diagram, force velocity diagram. So we have, for example, vibrating wires. Initially it's linear, and then it's you see the critical velocity, and I don't have really time to go into this, so it's because it's a cylinder, there is a flow around it, so you get enhancement of the flow, and because of that you get a pre-factor which is 1/3. So effectively you're breaking, you're already here breaking superfluid. And if you look at vibrating grid, it as well, it's linear initially, and then it starts to follow V over squared and produce turbulence. We produce turbulence here as well, but it's accompanied with emission of quasi-particles. And here in this linear regime, we can use them as detectors of turbulence. And if we are pushing them, we can create, say, excitation. It produces turbulence as a source of the turbulence. So how do we detect why helium-3 is different from helium-4? So it is fermionic, and so its dispersion curve is here. So we have a particle, quasi-particle branch, and we have a quasi-hole branch here. So it's effectively you have a dispersion curve which is just inverted. So it's done in excitation picture, and in normal fluid it would have been that dashed line. And because we have a gap, this is a gap where it's prohibited state. We can't reach it. So now we can have a normal scattering. So if, let's say, it scatters, if quasi-particle comes, it hits the wire, then it changes a momentum, so it flies out in different direction. Now you can have similar things with quasi-holes as well, and if it as well, it allows to have Andreev scattering. So it's similar to what happens in superconductor when, for example, if you have a border between normal metal and superconductor, when an electron approaches, it sees a prohibited state. So what it actually happens, it goes inside, it finds a paired electron with opposite momentum and kicks out the hole. So it appears that the hole comes out. So it's converted from the electron into the hole. And this happens almost with no change of momentum. So in this picture, if observer is stationary, and now if we start to move the observer, because it's a fluid, we start to have Galilean transformation. So the dispersion curve will shift with a Fermi momentum and a velocity of the observer. Same can be done with a fluid. If fluid is moving, your dispersion curves start to move. So implications then are, we can use this for detection. So imagine you have a vortex somewhere in helium-3, and then you have, if you're far away from the vortex, then you have this form of dispersion curve where the velocity is 0. And now if you consider this side of the vortex where the flow is going this direction, then the dispersion curve is tilted. And then if you have excitations coming, they sit on this branch, they can propagate, they have states where they can go. So on this side of the vortex, quasi-particles can travel, so it's particle flux. Now if it would be quasi-hole trying to move, it would move to this branch, but there is no states where it can fill, so it changes, it's Andreev reflected. And beauty about it, that it goes, it effectively retraces its path completely. So, but for if you would be sitting here, you would see the shadow. So not all the flux is going to make it through. And on other side of the vortex is opposite. So you will see that some quasi-particles won't go through, but holes will. So after vortex, you will see a shadow. And vortex core size is small. It's about 100 nanometers, but the shadow size is macroscopic. It's microns. At 150 microkelvin, it's about 6 to 15 micron. So you can start to observe this. If you would have a single vortex in a one cubic millimeter cell, its drop should be 2%. So it's quite large even from single vortex. So how we can detect turbulence? Let's say we have our vibrating wire, and we have flux of quasi-particles which is coming. Part of quasi-particles will be reflected, and we can measure fraction which doesn't make it through the tangle. So it will, the way it will manifest itself, that it will appear that the fluid became colder because there is less excitations is around. So signal size increases. This is how we can observe helium-3. So what beauty of this is that we can use, we don't need to put any foreign particles inside, and we can use condensate itself and some mechanical resonators in order to try to see what turbulence is doing. Right, so what have been done so far is that we had if we have 3 or 4 wires, when I'm just showing time sequence, let's say we turn the grid on, so we create turbulence. We can see that closest wire will produce signals, and it becomes steady state, and then if you switch it off, it starts to decay. So we can study three regimes. We can study how turbulence is developing, what happens in steady state on several wires, and then how it will decay. What becomes to the signal as well? So let's say if grid is off, we have a certain signal. Noise is very large. Once we start, once we turn the grid on, we start to observe quite large fluctuations on a wire, and these fluctuations are due to vortex lines to be present in surroundings. So when the flux of quasi-particles goes through, it sees the fluctuations of the vortex lines and reflects, and we can pick it up on a wire. So, and this noise is meaningful because we can take 2 wires, let's say wire 1 and wire 2, which is separated by 1 millimeter, and we can run cross correlation on the 2 wires. So it can show the propagation of turbulence between sensors. So this is an example of cross correlation between two wires. And if you change grid velocity, we can see initially peak is quite sharp. So there is a peak is quite wide and shift is quite small, but it's non-zero. So it means that the distance is fixed. So if shift is small, it means that it travels quite fast. And once velocity becomes larger, peak initially slows down. It's not well defined, and then it becomes more defined as velocity is increasing. So we can try to compute mean propagation velocity, and we get, so initially we get velocity on the order of 10 millimeter per second. It corresponds to rings, so vortex rings are emitted, and it's a lot. It's not a single ring. It's a lot of vortex rings which propagate. They hardly interact. And at certain grid velocity happens, transition happens when what today was shown as well is in a previous talk, some part of interaction. So we have 2 vortex rings. If one bumps into another, the smaller ring is ejected and it travels fast away. But if reconnection is such that larger ring is formed, it slows down. And if it slows down, there is a kind of avalanche effect. Other rings will start to bump into it, so you start to build a tangle. And the tangle is usually slowly propagating. So this is what will have, what is happening. As the velocity increases, tangles start to move faster. So what I have described, we had several wires, and this is kind of artistic impression. So grid emits vortex rings, and then at certain higher density, they start to collide and they form a tangle, and we can measure mean propagation velocity between the wires. Helium-3 is quite interesting as well because we can. I don't have much time to go into the details, but one can form using 2 wires and an enclosure. You can limit certain heat capacity inside. Helium-3 has quite low heat capacity. You can limit in a box, and you can try to make a escape hole. So it's kind of weak link. So you create a bolometer, which can be calibrated by depositing certain amount of heat. And then we have created a turbulence, and we looked how turbulence decay. So initially, thermal quasi-particles can leave quite fast, that order of several seconds, or 0.1 second time constant of the box. So within 1 second, all thermal excitations leaving the box, cooling down, but turbulence remained, and we can trace how turbulence decays. We can look at energy content of turbulence, which is decaying, which in classical physics, in classical liquids is very hard because of the heat capacity. So, and when we have done it, it was done a while ago, we have observed that grid can create turbulence. It's consistent with Kolmogorov-like spectrum. I don't want to say it's Kolmogorov spectrum. I would say it has a signature of Kolmogorov-like spectrum. Now, one of the recent works which was done in collaboration with Carlo, with Andrew, is try to look at fluctuations of the noise and try to do power spectra, and then we try to compare what line density, estimate what line density is doing and what the energy is doing. And we, let's say, done set of simulations where we created tangles of several type, same by injection of the rings, and then done some quasi more homogeneous tangles and try to compare what the spectrum is looking, what Andreev reflection is looking. And we came to conclusion, if you're interested to talk to, we can talk after that. We came to conclusion that the helium-3 tangles are polarized. So this is the reason, so they effectively move in one direction, and this is a reason why we observe Kolmogorov-like decay, because you need certain length scales. If one creates a turbulence at very low excitations, one can recover so-called, Carlo was talking about Wien spectrum, when it goes as a time decay goes as t-1 rather than t to minus 2, 5/3 in energy, at minus 3/2 in time. And Manchester data, which was working in helium-4 and they inject vortices at high speed again. It's one kind of in one direction. They again observe Kolmogorov-like decay. So idea what we would want to try next is to try to create high density tangle which is stationary. And the idea behind this, in order to do that, I'll talk about this, sorry, later. We have two grids. I will come back to this. So we can, if we have a one wire, we can monitor what the kind of statistics of the flow. We can see whether there is mean flow if there is two wire using cross correlation. We try to visualize turbulence. So we've done a so-called quasi-particle imaging. So we have a box which creates, we use it only as a furnace, as a light. So we can put heat in, and then it will create excitations which will start to come out. So beam of quasi-particles. It's broad, it's very broad. We spread, we have a wire which will create turbulence, and then we have a 5x5 array of tuning forks, but they are oscillators which can detect again quasi-particle flux which coming through. So idea, I will show just the result. So big picture is here. So we heat up the box. We put set of quasi-particles coming out. It's a lot of quasi-particles coming out, and we create a vortex tangle, and we try to look what happens on a detector plane. So here I showed it as just as a velocity of the wire, and we have fractional screening. It's amount of turbulence we have. For simplicity, I just showing what diagonal pixels are doing. This E1 was that, we could not use it, so it's a 24 pixel. So we have diagonal pixels at different color. So initially nothing happens, and then only at certain critical velocity, when we reach, we start to observe the turbulence signal is observed, and then it plateaus, and then it becomes about 20 millimeters per second. The heat becomes so large that we cannot longer measure. And similar things can be shown on just as a picture of the array itself. So we have a wire itself. This is roughly where the center of the box is, like a hole, is located where quasi-particles are coming out. And we can see that at low velocity, it's about here, the production is very non-uniform. So most of the, so red color is positive signal and blue is negative, but it cannot be negative reflection. So it's what it indicates noise, how much noise we have in a system. And so we can see that most of the turbulence which is produced here, which was quite surprising to us. And then as it increases, it's mostly turbulence is produced above the wire. And only when we reach quite high velocities, it starts to get quite uniform. So we don't quite understand this because wire is supposed to be 4.5 micron and 3 millimeters diameter and 3 millimeter distance. It should be quite smooth, so there is no reason why vortices should be dominantly produced in top of the wire. So, but just production, because naively I would expect if it would be cylindrical surface, any vortex that can be on it can spin around, for example, on a cylinder. So it should have been produced everywhere, but we're still seeking for the proper theoretical explanation. So if someone is interested in modeling wire and a vortex on it, pinned, it would be very beneficial. It should be, but it could be that if there is spinning centers, but the pinning helium-3 size core size is 100 nanometers, so it should be pinning size should be 200, 300, so it should be quite large. And even if it is possible, but if it starts to oscillate, usually the vortex is elongated and then it should pinch off. And then I don't really see why it would fly, because if it would fly, once it starts flying out, if it flies in any direction underneath, it would produce screening as well, because we are looking at line of sight which comes out through. So it's quite surprising that it develops kind of shadow predominantly on top rather than bottom. Yeah. So I leave it as a open question at the moment. Yeah? So what we would want to do next, we would want to put two grids and create a much larger array using tuning forks. So the idea is that you use vortex rings. We can calibrate both grids, so we know where the only rings are propagating. As I say, they can travel at least 10, 20 millimeters at low temperatures. So an idea is to collide them in a center and create a stationary tangle with high density and see whether then scaling will change in this case or not. And in order to visualize what is well happening and how it's distributed, we would like to create 90 pixel camera. Technology's principle is there, which we should be able to do it. Downside of the camera made from either vibrating wires or tuning forks, which we use, is the time resolution. Because width of the line, width of the tuning fork can be about, let's say, 0.1 hertz. So it implies that, or 10 hertz, so it implies that time constant is maximum 0.1 second. So it becomes relatively slow. If we want to go faster, we would need to use higher frequency objects and then they tend to have larger bandwidths, larger damping. And so we want to use nanomechanical oscillators. They use higher frequency but larger widths. This would allow us to increase time by 2 orders of magnitude. And they're supposed to be, what I haven't talked about, when you're in helium-3, sensitivity to flux of quasi-particles goes inversely proportional to the diameter of the wire as well. And then it means that they should be more sensitive. If we reduce it from 1 micron to 100 nanometers, signal should be boosted by an order of magnitude as well. So it would help. So we started with this, we started to develop nanomechanical beams. This is how the two parts of the talk are related. And if we look at the length scales in helium-3, so we have, on one side, we have a tangle. Tangle has characteristic size of about 1 centimeter. Then intervortex distance, which we estimate, is about 100 micron. Then size of the vortex rings are about 10 micron. Vortex core in helium-3 is about 100 nanometers. I showed that Kelvin waves are 10 nanometers. In reality, they span the larger range, because if they're large Kelvin waves, they process the vortex itself. And we have quasi-particles, which are they're much smaller. So we are trying to kind of measure all the range, trying to cover with the devices all the range. So what we have a tuning forks which cover about 100 micron. Then these devices were developed in Yunsuk Lee. They're about on plates 200 micrometers. It's Yunsuk who done them in helium-3 to try them and in helium-4 to observe the vorticity. Our traditional wires were 4 micron size diameter, and then 1 micron was smallest. Now we have with Dimazmeev have done by hand some wires which are 400 nanometers. They're just by stretching same wire, same superconducting filaments through the orifice. One can make wires thinner and then strip it and then create up to 400 nanometers thin wires. But Helsinki group is trying to do pedals, and I think in Prague, David Šmaranza is trying to work with a 10 micron wires, and where it has several nanometer, 100 nanometer, 200 nanometer size. We try to do, we try to create nanobeams. So the lengths would be from 70 micron to, let's say, 400 micron long, but dimension is about 100 by 100 nanometers, and vibrate them. We need to create, of course, the devices in themselves are insufficient, so we want to create kind of arrays. So camera is one thing. Our tuning forks are arranged in array. 5 of them, because they have different vibrating frequencies, they don't overlap. We can address them individually on a single bus. So it's quite convenient. We recently obtained the nanobeams, array of nanobeams. This was done under, again, microkelvin. They were manufactured actually here in France, is in Grenoble. It's a group of Eddie Collan who produced them for us, and we put it, I think, a month ago, them in a cryostat to try to measure. And we use bolometers, which are, so this would be sensitive to the turbulence itself, and bolometers will be used for energy content because they're sensitive to bare quasi-particles as well. Sensitivity is quite large. So we are trying to cover all the length scales. But you know, to put everything into helium-3 is very complicated. So we are trying to, because temperatures are so low, its closing time is about several months by the time you made cell, by the time you closed. It's not very different from Shrek, which was shown yesterday. I don't have a video to show you how it's closed. But so we tend to test everything in helium-4 to make sure it's working. And helium-4 in itself is fascinating. So usually we start to test something and get stuck because some physics is discovered. So I will describe next what we do with nanomechanical beams. So we have a nanomechanical beam. This is, let's say, 100 micron long, 100 by 100 or 130 by 130 nanometers. They're placed in magnetic field, and again they're driven by AC, so similar method. And then we pick the Faraday voltage. Most of the time so far, beams which we used, they were normal, so we get offset from background as well, from resistance. To get them superconducting is quite challenging. Magnetic fields are quite slow, signal becomes tiny, but we are working on this. So the beams themselves, if they are initially quite nice and linear at small powers, and then once you start, it's in vacuum, this measurement done in vacuum, and once you start driving them very hard, they start to show Duffin style instability. They become not nice Lorentzians. So it becomes much harder to work with them. They can, we use as one of the first things which we done with beams in 2017, we put them in helium-4, superfluid helium-4, and try to go through the transition to see that they work as a detectors. They follow hydrodynamics quite nicely. I still prefer the conventional wires. They're much easier to work. They're, I think, more robust. So if anyone, I'm not sure that I would switch for nanomechanical beam just to go through the T lambda. It's not efficient. I have some more beams, and it can be quite messy. So this was a quite nice sample. So we as well tested them in very low temperatures in helium-4, and they're sensitive to rotons and phonons. But I'm going to skip this part and we'll concentrate on a turbulence. So what we have done, we had set of beams, but we use only one of them, and we have a tuning fork which we use to produce turbulence. So we excite tuning fork quite hard, we drive it quite hard, and it starts to emit vortex rings and then produces a tangle, which how it disperses, we don't know exactly. We just know that if you put sufficient power, you create turbulence. I think it's done quite often. I think the specialists in this are the Ladix group in Prague. They who measured using second sound, for example, how it propagates and what's happening with it. We just put it as a means of creating turbulence. So the way we know that the fork is producing turbulence, what we see with force velocity, again characteristic in vacuum, it goes almost linear. There is slight deviation from linearity, probably because of heating. We don't know exactly what temperature of the fork in vacuum is either, so it doesn't cool as nicely. If you do it in helium-4 at base temperature of the fridge, at certain velocity you get a plateau. So we don't know what we create, but again, from experience and from other labs, one can safely assume that it's a turbulence which is produced. So initially we started so the shape is Lorentzian. So with what we started to do, we started to sit at some point and just try to observe time sequence as we are trying to drive the fork. And what we started to see some spikes. And spikes were different depending on a location that we were. And so what we have inferred from this, then it looks like the peak is jumping. The normal peak where it would be, depending on as vortices start to approach it, they would start to jump. But this picture is quite unsatisfactory because it's very difficult to extract any information. So what we have done next, we had a device which is multiple frequency locking, so it can measure 42 frequencies at once. So effectively what you do, you create a comb of frequencies. So it works on multiple of frequencies. You give a base frequency and then you can work on multiples, because then you can get phase locked. It's a commercial device which we used. And then downside of it is once you create a frequency comb, you're limiting your time resolution, because it's inversely proportional to the time between the frequency comb. And then what we started to observe that beam. This would be a baseline of the beam where it would normally sit. If nothing, if we don't produce fork. Once we start to excite in fork, we started to observe series of events, and we are talking about thousands of them. We can just keep it running. And then it was producing that initially was some rise, and then it was a plateau, and then it would be sharp drop from the plateau. And for this beam, we just saw effectively 90% of the time it was just two levels. It was never going higher than that. So the way we have interpreted the results, that we have lower part is vortex-free region, so there is no vortex at all, and top part is when the vortex is fully trapped along the whole beam. And it's if we would stop the turbulence production at the right point, this state would survive for a week and a half. So it would not change. So it's definitely stable state. But as soon as you turn turbulence production on a fork, it would drop, and then picture started to repeat. So idea behind it, and the way we interpret it, is that initially the vortex is on a rise. Vortex is somehow trying to approach the beam in order to get trapped. We never can get, it's very hard to trap two vortices, to have double. In principle, it is possible to have double quantization of vortices on a beam, but in a bulk itself is in helium-4, it's energetically unfavorable. So we believe that we only trap single vortices. And then the sharp drop we associate with another vortex line is approaching the vicinity, they intersect, and then they just peels off very fast. Usually this process, if you compare it to what observed in optical measurements, they are comparable. I'm doing for time, I have six minutes left. So this was our interpretation. We tried to look at some statistics as well. So we looked at initially we tried to change density, we tried to change fork velocity with the onset, and we started to look at the time between how long it would stay without vortex, without trying to trap the vortex. And the higher was production rate, the shorter time became. So it was definitely correlated to number of vortices which is produced. And what one can see the statistics here. It's summarized in the. It's followed Poisson distribution as far as I remember. And then we tried to look at the lifetime of the plateau, and what we observed initially, we were quite surprised that it didn't depend on a density of vortices inside, which is a bit counterintuitive. But later, I think we came across paper from Maryland group in 2019, and they saw distribution of time, distribution of lengths, how the vortices intersect. So our interpretation is that once it's there on a beam, it chooses the nearest vortex. Once vortex is nearest passed, and this can be quite random. So how many vortices are located next to it? So it chooses the first one, and because then its state is destroyed. So this was our explanation. So this was so this demonstrated that the beams are sensitive to the vortices. But so far we have two configurations. We have configuration when beam is clean, and beam is and vortex is aligned fully. So what we try to do, we try to trap vortex which is perpendicular, because then you can start shaking the beam, and then you can try to see how energy will dissipate along the vortex line. This is what we are working on now, but this way we start to run into some difficulties. We can trap such states, but problem is that an interpretation of the analysis is very tricky. And the reason why it's tricky, because once you start to do power dependencies, say beams themselves are, they can be linear at low drives, and then become highly Duffin-like. So we measure both. We measure not only amplitude, we measure phase and magnitude. So Vx and Vy components. So it's phase-sensitive measurements, and we can now describe beams quite nicely using the Duffin term. We can, for example, this was velocity of the beam changed, and then we can see that frequency is staying constant despite it appearing to. So it was 650. This way it was locating, and maximum is now here. But actually, resonance frequency is constant. It's just due to Duffin. The Duffin term at high amplitude, the peak appears to shift, but actually frequency is staying the same, and the width of the peak is staying the same. So we can fit. We have now robust fitting we can do, and alpha nonlinearity coefficient we can extract. It's constant as well for a beam. Initially, at lower part, it doesn't matter what it is, because its contribution is quite small. So we can extract force velocity, which is linear for the beam still. Now, if we trap the vortex perpendicularly, then what we start to observe that in addition to the behavior, Duffin oscillator behavior, we start to see that circle start to become it's not a circle anymore, and usually it implies that you have the damping start to become non-linear. So we are trying to work on one side on the models which explain how the damping takes place in order to extract damping coefficient with time. So we introduced, this was done as a fit, but you can see there is a kink actually so this model is not quite adequate, but one can try to get it, but one should work on it. So one set of data which we have analyzed, we trapped many events, is, so we have force velocity where we have vortex is, there is no vortex state which is parallel, and vortex state which is perpendicular, and at some stage the pink one is magenta, it's where it's perpendicular. We start to see onset of damping, and then so it stays stationary. It looks like there is some other, even damping increases initially higher and then it goes back, and then after certain threshold it starts to, we can again try to push beam, increase the velocity. If the way fitting the shape, line shape looks like this, so it looks complicated, but if you look at the diagram of Vx versus Vy, you can start to see original and low damping state and high damping state, and we can try, this is how we extract the data. We just fit them two circles independently. And if this is how it's plotted, so we can put adjusted force and adjusted peak velocity. If we calculate the power, force times velocity, or excess force versus velocity, we can extract power, and if we divide it by frequency, we can obtain energy per event. I'm not going to show it on a plot, I will just state it verbally, that it looks like the energy which is correspond to the per cycle is 10 Kelvin. So it's very close to a single Rotan emission. I know it's a very bold statement, hence we are trying to look at it and from theoretical point of view, but if from trying to contact, what I mean, trying to contact theoreticians and trying to explain how it can be possible that we can emit a single Rotan, for example, in per cycle. So this is a kind of state at the moment where we are. And the last experiment which we started to do, now again, we changed the geometry. If before beam was above the plate, now we have two beams. An idea is to trap vortex, let's say, across two beams and trying to see how they will start to interact between themselves. So geometry is quite different. And here we started to look at, just started, it's 2 weeks ago, we started to look at the traces. It looked like there is some maybe coincidence at certain parts, but we need to run cross correlation in order to see how actually whether they really interact or whether it's just coincidence, and try to trap event which will be across both vortices. So I think this is effectively all I wanted to say. It's a summary is that we are trying to use nanomechanical beams in helium-4 because they're smaller size and should be sensitive to vorticity. And helium-3, despite being at very low temperatures, it offers route to visualization of turbulence without producing any, putting extra particles in. I thank you for attention.
Thank you, Victor. Any questions?
Yeah, thank you very much. Excellent talk. Thank you. I did not understand why did you need a second grid? It had the first grid and then your probes, and then you had the second grid. And if necessary, why did you not go to different sizes, different models of the grid, multifractal or whatever?
Thank you. But so I have not explained to this. So emission of the vortex ring, it's not like classic, it's very different from, emission is very different from classical turbulence, where the grid size determines the size of vortex ring. It's determined by frequency. Frequency of the grid, so it's more like a transducer, effectively, oscillating. So the size of the ring is determined by the frequency of the grid, and they're usually all within around 1 kilohertz. So the ring size, which is emitted, are almost identical. And then the reason why we put second grid is that when we create turbulence from using the single grid, it goes on both sides and propagates away. But you have a effectively large-scale flow generated. So idea is if you would create, and then we believe that this leads to appearance of Kolmogorov-like spectrum. So if you put second grid and put and rings will be flying in opposite direction, they will collide in a center, but then will be no mean flow. So tangle will become stationary. Then we can kill off excitation and start to look what happens to the some so goes, thank you.
Thank you for a nice talk. For these nanobeams in helium-4, do you ever see any fluctuating state between laminar and turbulent flow, like, for example, what Shepe saw with oscillating spheres, or does it always just go smoothly from kind of laminar to something probably turbulent?
So very good question. So we try to use them as detectors. So we try to drive them mostly at low velocities. Once we have trapped the beam or trapped the vortex, then we can try to push. We start to look at amplitude, what happens with a single vortex which is trapped. But we tried them just to drive them in helium-4 to high velocities. So far, we have not seen production of turbulence by the beam itself.
So it becomes stuffing, but it's still
linear. It looks like linear dissipation. Only when we trap something on, then we start to see non-linearity. At least this is picture so far what we have. So it looks like, and if you estimate critical velocities based on papers, it should be on the order of 1 meter per second. It should be quite high based on motion steady flow because dimensions are small and on oscillations as well.
Thank you for your very nice talk. So I wonder, in my understanding, in helium-3 B phase, so there is one transition shape of vortex core from single core to double core, and that change of shape. I wonder, change of shape affects the detection of vortex core by vibrating wire. So, have you any idea?
Yeah, we have not tried it. You're absolutely right. Actually, I kept vortex core is more in helium-3 is more complicated. Actually, it's 2 half quantum vortices inside the single core at low pressure where we work. But as far as we know, it doesn't affect the dynamics. But if you can change vortex core size to larger, if you go to higher pressure, about 20 atmospheres, we have not 20 bars. We have not actually done it. I know that Helsinki group more looked into this work that like Volodya Yelsov.
Thanks.
Well, maybe I have my own question. How do the mechanical frequencies and time response of the system compares to the Kelvin wave length scales and frequency that you can get between 2 beams, for example, here?
Short answer is I don't know. Yeah, but we are not quite sure how it will manifest itself. Actually, to say even more, frequencies of Kelvin waves, they can be calculated by size of, it's about 100 micron, so we can estimate them. But the beam's Q factor is very narrow, so it would be, and they're separated. So we will not be able to see the overlap. Only thing which we can see is change in damping and shift. By shifting frequency, we should be able to see how much estimate how much of the vortex, how much of the beam is covered by the vortex. This is what we are trying to work on. And second, the only way to check is how damping will be affected. But we have no theoretical picture. So if anyone can help us, this would be greatly appreciated. So it is tricky. It is very tricky.
Okay, well, you have a question? Any other questions? No? So maybe we can thank again Vickor.
Thank you. Thank you.